we are about to get started. So first, welcome to the webinar. Thank you so much for attending. Just for some housekeeping, this is being recorded, so everyone who has registered will receive a recording after the webinar. Also, we'll leave some time at the end for Q&A, but also feel free to ask any questions you have as they arise in the chat window, and I'll be picking some of those out to ask Chris while he's doing his presentation. So just for some background, I'm Nate Stewart, the VP of Product here at Cockroach Labs. I'm here with Chris Chambers. Chris is the Cloud Database as a Service team lead at Bose. He's passionate about creating tools and techniques for better software engineering and wants to build new ways to write and reason about distributed systems. His team at Bose has been building a cloud platform on Kubernetes as a foundation for their new work on cloud-connected devices. Chris's team is responsible for providing microservices developers with a uniform interface to databases. So before we get started, we like to just wave to everyone so you know that you're talking to two human beings. So hey, Nate Stewart here.
Hi, everybody.
All right, and Chris, with that, I'll let you take it away.
All right. First, thanks everybody for coming, and thank you to Cockroach for having me. I am honored, and hopefully I'll be able to work this thing. Here we go. So this talk is about building databases on demand with Kubernetes at Bose. Who are we? We're Bose, the company. I think this is a household name. I probably don't need to explain too much. But within that, I work on a larger team called Galapagos, which is an initiative to bring Bose's software into the 21st century in a way. In the past, we've been very focused on embedded software that runs on speakers and headphones. And we need to modernize and bring cloud-connected experiences to all our devices. So I'm part of the team that is heading up that initiative. There are maybe 50 of us now, but that grows all the time. And then within that team, I'm on a smaller team called DBaaS, Database as a Service. So that's me, Chris Chambers, Elena Shaw, who joined 6 months ago or so, Carlos Bonilla, who joined in the last couple of months. And I worked with Fatih Chetinkaya. He was sort of my partner in crime for the initial development on this work, but he's gone on to other things in Bose. All right, so our technology stack kind of defined what choices we could make. First, we're running Cockroach. Of course, this is a Cockroach presentation, so it wouldn't be right not to mention them. Elasticsearch, we make available Kafka, MongoDB, Postgres for when you need a low availability version of Cockroach, we could call it, and Redis for when you need to share memory with other applications. Underneath all that is Kubernetes, which hosts essentially all the compute that we do at the moment is on Kubernetes. A few things maybe are still running directly in AWS, but we move more and more toward Kubernetes all the time. We're using the service catalog, which if you haven't heard of this, it's a kind of abstraction layer that allows external services especially, but really any service, to surface into Kubernetes in the same way that a pod or a deployment or a stateful set would, but without exposing those details. So behind a service catalog instance, there might be an AWS RDS instance, there might be a Cockroach instance running as a stateful set in the same Kubernetes cluster or in a different Kubernetes cluster, or really anything else, even cross-cloud, for example. We're using Helm to deliver the databases. The breadth and depth of charts that are available as a starting point, and the templating that Helm provides, and the release management made it seem like a natural place for us to start, but we've built up significant infrastructure around Helm. And then finally, we are doing disaster recovery with a tool that was called Arc, I think, at this time last year, but has been renamed Valero. And what this is a tool that essentially runs cron job schedules and takes snapshots of Kubernetes resources and crucially any attached volumes. So EBS volumes in AWS get snapshots when Velero runs. And that's the way we provide disaster recovery capability for the databases that we provision for people. One of the main things that we were charged with providing was an interface that was straightforward to use and would be uniform across multiple kinds of databases. A lot of what we're trying to do with Galapagos and Sybose is to create low friction ways for developers to work and to use things which they may not be completely familiar with at first in a way that's quick and easy for them. We wanted this to be self-service, so it should be possible for teams to stand up a database in just a few minutes without any help from us, reading along in the wiki for instructions and typing in just a few lines of declaration. It should be declarative so that you can repeat your deployment in any environment, whether you're doing a feature branch to quickly test something or whether you're preparing to go to production. The declaration about what kind of database you need should be the same, and only the scale and other kinds of parameters should change. And that should all live right next to your application so that the code that uses a database is versioned alongside the declaration about what kind of database and the parameters that you use. So for us, that looks like this. This is a file called micro.yaml, which is processed by an internal tool. In the intervening time, several tools have popped up that do this kind of thing. But a couple of years ago when we were getting started, the choice was a little unclear, so we wrote our own. It's possible we'll move to one of the more standard ones in the future, but for now, this is what we're using. Here's what it looks like to declare a database using the framework that we built. In the components section of Micro, you list things like, I want these containers to run, which in Kubernetes is mapped to a pod. So we added this new kind of component called a service. And then you give it a name so you can refer to it. You say what kind it is, in this case, CockroachDB, and which plan you'd like to have. So we have default plan, which is like, I just want to experiment. Development, which is a realistic, but probably overcommitted database where we don't guarantee that you'll have a certain amount of CPU or memory, but we try to provide you with quite a realistic example of the database. And then finally, production, where all the resource limits are completely reserved. There's very little overcommit because we don't want noisy neighbor problem in production. And this is, essentially the gold standard. We use this for production workloads and then for anything that's leading up to production, like a staging environment. So that's what that looks like. We want to keep this minimal. That's this is the least you can do, and that's about 6 significant lines, which we think is not bad. Moving on, you then need to connect to that database. So when the deployment begins, we'll process the declaration that we just saw and instantiate a database. In this case, a Cockroach cluster will come up, will form itself, and we'll do some kind of basic initial work, like applying our enterprise license and setting a few things up. And then we deliver to the application as a standard Kubernetes secret the coordinates and credentials for that database. So in the case of Cockroach, the host, the port. For Cockroach instances, which are running behind SSL, we deliver the certs needed to connect, that sort of thing. And these can be bound into the container just like any other secret, and the application can use those in whatever way it wants. And then finally, we have a declarative way to schedule backups. So for our default plan and development plan, backups are turned off by default. For production, they're turned on by default. But developers can override those with just a few settings and choose what kind of durability they would like to have. There's really no limit here except for the amount of space that's used. And we work with the teams to make sure that they're not creating a backup every 5 minutes and keeping it for 3 years, that sort of thing. So there are things that we did not try to do. We didn't try to do any within database multi-tenancy. So we don't provision a Cockroach, let's say, and hand out different schemas to different teams within that same Cockroach instance. We do multi-tenancy at the Kubernetes worker node level. So even in production, you might be scheduled alongside another team, but all your resource limits and reservations are completely reserved. So there shouldn't be a noisy neighbor problem. At least we haven't experienced much yet. We currently don't support very dramatic topology changes. So if you spun up, for example, a non-sharded MongoDB and wanted to switch to a sharded configuration, that's something that we would require you to do a migration on right now. We're looking at that kind of migration as something we could bake in and make like a one-click operation, but it seemed like a pretty big lift for very little benefit at first. We haven't done a lot of intensive tuning. So far, our loads are low enough. You know, we're talking about many thousands of requests per second, not many tens of thousands or many hundreds of thousands. So we expect as the load grows, as more and more of our devices become cloud capable, that we'll need to do some intensive tuning, in particular, learn more about how Docker and Kubernetes' network layers work to get the kind of performance you might need for a very high scale application, but we're just not at that stage yet. And another thing we haven't really tried to address yet, although that since I originally wrote this presentation, this requirement is sneaking up on us. We haven't tried to do very fine-grained access control. So when we provision a database for a team, they're given the keys to the castle, and how they want to parcel out access to the database is really up to them. The only access control we put in place is a network policy from the namespace that holds the database to the namespace that uses the database. But we have plans to be more fine-grained there. So now that I've told you what it is, you must ask yourself, why would you do this? Amazon has perfectly wonderful managed databases. Why would you run your own? It's a lot of work. It's difficult to verify the quality of a lot of these databases, especially at scale. And running databases inside Docker containers is an area that's still maturing, and running containers, database containers inside Kubernetes is maturing even more. So why would we take this on? As I said, we wanted to provide a uniform interface. Even within AWS, the interface to different kinds of databases is not so uniform. They've grown over the years, and different capabilities have been exposed with different databases. We wanted to give developers kind of a really point-and-click experience. Not that they always need that, but just to reduce friction for the initial cost of getting a project up and running. And we wanted to reduce the operational burden for developers. So we certainly did not want anyone to feel that they should run their own database. In particular, not as a stateful set in Kubernetes, because we learned there are a lot of things you need to know to do that correctly. But we definitely wouldn't want people running their own instance on raw EC2, and even provisioning on their own dime or time an instance from AWS managed services. It's a thing you have to know about and manage. You have to opt into upgrades, and you have to understand how the monitoring works. It's not part of our monitoring plane or anything else. And so we wanted to avoid extra work that would come from that kind of thing. I mentioned this a little. We wanted to integrate also with, we're running Kubernetes, so of course we're running Prometheus and Elk Stack for logging, and running our own databases in a uniform way. Inside the cluster especially, it makes it very easy for us to hook in metrics and logs into the existing infrastructure. And finally, a goal that I'm not sure will ever come to fruition is that we want it to be cloud agnostic. There's a feeling that we would want to branch out. We're currently running on AWS, but maybe we want to branch out to Google or to Azure as their offerings mature. And we wanted to start at least by defining the interface for microservice developers to be agnostic of those choices. Even if we start to adopt managed services behind the scenes for DBaaS, we want to present to the developers the interface that can be universal to all the clouds that we might choose in the future. So I don't know if that's enough justification, but it's how we made the decision. And we went ahead with it, and we're in production now. So how did we do? There were some good things. It went okay. None of the databases have exploded yet, or at least not in major ways. That's a bonus. We're now running 20 production instances. This number may be a little stale. It could be a little higher now. And I like to think that by the time you get to 20, you are actually paying for yourself. There were 2 of us on the team. Now there are 3 of us, and we're looking at another couple. When you're managing 20 things, I would think that we've taken enough off the plates of microservice developers that maybe we're getting to the breakover point where this is worth it. And if this number goes up as it has been going up, then we'll be well in the black soon enough. We've got 150 non-production instances. I hope that this kind of thing is really helping people. I know from my personal experience writing microservices, one of the real pains of running integration tests, for example, or doing experimental work, is that spinning up complicated databases can really be a blocker to get started on something. So hopefully that's reducing friction. And so far so good. We've had, with the exception of the asterisk, which I'll just mention, we've had 99.996% uptime, which is better than I thought we'd be able to do. The asterisk is there because we had an unexpected interaction between a firmware release that caused one of the Kafkas that we provisioned to be dramatically under provisioned on space. The devices started to send us payloads that were, I think, about 10,000 times individually larger than what they had promised to send. And so the 6 or so terabytes of Kafka space filled up within a matter of hours, and we experienced an outage while we resized those drives. So apart from that one, we're pretty good uptime. There were a few bad things. When we shipped, when we were building this, the service catalog was in alpha. We figured no big deal. We were building this. We have runway until later this year. The service catalog is rapidly moving out of alpha. Kubernetes is being upgraded. No problem. Except there is a problem. We didn't take those upgrades for internal reasons. We stayed with Kube 1.8 until we released, even though 1.9, 1.10, 1.11 were released. At some point, the service catalog became dependent on Kube 1.9. So we've been stuck in an alpha version all this time. I would say, obviously, this is not the service catalog's fault, but it is, even though it seems like you have plenty of runway, maybe it's a mistake I would never make again to ship, to even consider alpha software that I suspected would move out of alpha in time, because it didn't for us. We found a bug in Kube 1.8 API aggregation, which the service catalog uses. This was a fun one. If the service catalog is down, or any API aggregation is down for a certain amount of time, Kubernetes sees those resources not as unavailable, but merely as non-existent. And then the Kubernetes garbage collector starts to run and collect anything that's associated with them. Well, the secrets I mentioned earlier that are delivered to the application are owned by parts of these resources that are managed by the service catalog. And within the period of about 5 minutes, we lost every single database secret in the cluster. So that was quite fun. The real trick was, it doesn't hit you immediately because most of the containers have mounted their secrets already. It only hits you when you try to roll a node or roll a pod and it can't mount a secret again. So that was a fun one. We're still vulnerable to that because we're not to 1.11 yet. And so we tiptoe around a little bit. And finally, something we failed to do, and something I would recommend to everyone, is to build escape hatches into complex systems that you build like this. It's a wonderful goal to have perfect automation. You want people to be able to completely serve themselves and have no manual steps, no interaction from your team except in emergencies. But there are times when, especially during emergencies, it's crucial to be able to override the automatic machinery and step in and say, please don't do that right now, we're having a problem. We ran into a few cases where mechanisms that were meant as self-correction mechanisms actually prevented us from manually correcting a problem. And it would have been good to have an escape hatch that got us out of that situation. There were a few ugly things. There always are. In particular, Java programs are very difficult to containerize, especially databases, I think. So everybody knows about the maximum heap size of a JVM application. What I didn't know is that at some point, I lost track of the JVM, I guess. They moved the class metadata out of the heap and onto the native heap, so that when you specify XMX to fit within a container's memory budget, you may actually exceed the budget because of classes that are loaded by the JVM. So tuning that was a trick. Newer versions of the JVM respect C groups, which you would think would solve this problem. Unfortunately, as far as I was able to understand, the JVM uses C groups to set XMX and does not leave room by default for the native heap for the very same class metadata that bit us the first time. So that was fun. There were a number of things to work out with Java that we kind of struggled through and found it was a little difficult to find good resources on what's the best practice there. Kubernetes is extremely asynchronous. You hear this, and it sounds sort of like a good thing. It's an eventually consistent system. You ask for something, and Kubernetes does its level best to eventually give it to you. And in most cases, it's able to do this. In most cases, there's no problem. But there are some things I'll talk about on following slides that bit us with the asynchronous nature, and things that you maybe wouldn't think about at first until you start to get complaints. And then finally, much as I love Helm, we ran into some problems that could have been avoided if Helm's templating system wasn't a text-based system, which is agnostic of the fact that YAML is an object document-based system. It's very easy to have a small indentation problem in text-based templating that completely ruins a template, but it'll succeed in some cases, and then when a certain shape of data comes in, completely fails. So it would have been nice maybe to have a templating system that understood what kind of document we were trying to build. All right, now that I've told you how great this was, or maybe how bad it was, if you're listening to this talk, maybe you're interested in doing something like this yourself. So let's talk about what you'd need to know. Unless there are any questions at this point, actually, let me pause. Nate, anybody?
Right now, there are no questions.
Okay, great. I'll keep going. All right, so there's some things about Kubernetes that are not trivial to understand. A lot of these actually, I'm listing them here because it's things that we experienced bugs for a while and had no idea actually what was going on. So we have earned the right to talk about these because we track these down in some cases ourselves. Of course, you can always find the GitHub issue where some other poor soul has done the same thing. But anyway, I'll mention it here. Init containers, which you may be familiar with in pods, always run at the beginning of a pod's lifetime. It's meant that init containers run serially in the order that they're specified, one after the other, and then when they have finished their work, the main containers of the pod come up. It turns out the default setting of kubelet is quite sane and quite ordinary. The reclamation in Docker of containers is based on the amount of space left, whether there's pressure. Generally containers kind of last, they stay there even after they've finished. They stay there as long as they need to until there's some pressing reason to get rid of them. The team that's one level below me in the stack here at Bose changed our kubelet settings to what appears to be quite a sensible setting, which is that when a container stops, let's just go ahead and remove the record of the container from Docker pretty quickly. I think it seems to happen every 60 or 90 seconds for us. So as soon as a container goes away, it's reaped without waiting for memory pressure or disk pressure or anything like that. That sounds perfectly reasonable, except Kubernetes' record keeping about which init containers have started running and have finished running is based on the container records that are in the Docker daemon. So in some cases, I don't think it's universal, but we have definitely seen it happen. When the init container runs and then the real containers begin to run, if Kubernetes notices that the init container is a finished container and kubelet deletes it, then Kubernetes will again run the init container because it looks and thinks, oh, the init container must not have run. I don't see a record of it. So we had some init containers which were within the lifetime of a pod, not idempotent. So they would come up and do some work that if they did it again, it would actually be invalid to do. We learned quickly that you have to make them idempotent. I will say this is something that's a little specific to our configuration. We definitely exacerbated the problem by changing those kubelet settings, but I see no reason why this couldn't happen in any configuration. As long as there's enough pressure for Docker, for kubelet to need to remove an old finished Docker container record, then this is possible to happen. And maybe even worse, we saw it immediately because the reaping happens so often in our stack. But even worse for teams that are using the default settings, it could be weeks. And then suddenly an init container runs in the middle of the lifetime of a pod. And if you're not idempotent at that point, you may have a real problem and a difficult problem to understand. PVCs are only ever created by stateful sets. PVCs, for anyone who doesn't know, are persistent volume claims, which is how you get a persistent volume, which is how you get, in our case, an EBS volume attached to a stateful set. The stateful set manages these for you, except only to create them. It's nice and safe that it doesn't delete them, but at times you may need to clean them up. So we found ourselves with a bunch of orphans because we failed to understand the semantics of stateful sets. We had, hundreds of PVCs that were attached to nothing, just lurking around. So now when a database cluster is torn down for good, we clean up the PVCs. And after a durable scale down, that's a scale down where you intend that the new smaller cluster size will stay that way for a while, we manually clean them up. And it goes without saying, please take a backup before you delete any PVC. So that was the grab bag. Here are some things that are more specific. Kubernetes has liveness and readiness probes, which I'm sure you're already using if you do microservices. In microservices, everything's quite normal. You give typically an HTTP endpoint, and Kubernetes dials up the HTTP endpoint and tries to do a get. And if it gets to 200, I think everything's fine, and maybe all other codes are considered a failure. There's another kind of probe called exec. So this is for programs that don't expose an HTTP interface at all and wouldn't want to expose one just for the purpose of health checking. So there's the possibility to exec into a container and run a command that would assess the health of that container. This is very common in databases. The problem I'm going to describe actually doesn't affect Cockroach because Cockroach's health is HTTP based. So thanks for that, guys. But it affects Redis, Kafka, Elasticsearch, and Mongo in our stack, and Postgres as well, all of them except for Cockroach. So in this top example, you're allowed to write timeout seconds 5. I've given the exec command, Redis CLI ping, very simple. This is stripped down quite a lot, but it's reasonably representative. And I've said, if that doesn't work within 5 seconds, just give up. This is allowed, but it's not used. Even today in the Kubernetes source code, this value is not referenced anywhere in the exec probe runner. So what will happen if Redis CLI ping in this case were to hang, a Go routine will permanently wait for the command to return. In some cases, the command might never return because the database is in an incredibly bad state. And because the command doesn't return, Kubernetes, and it doesn't time out, Kubernetes can never decide that the pod is bad. So it can never remove it from any load balancer. It can never decide to restart the pod. All it can decide to do, and this is very unfortunate, is wait period seconds and spin up another go routine, which of course will make the same call and probably block, until there are hundreds of thousands of paused go routines trying desperately to get Redis CLI ping to work. But in fact, the Redis server for some reason is hung and it's never going to respond. This was difficult for us because the behavior that you see has nothing to do really with this situation. What you see is parts of Kubernetes like running out of memory, reporting really high go routine counts, very strange behavior, and it's hard to pin it on the liveness probe. But we finally figured out, just really through reading the source code, that that value is not respected and that at times our exec commands were hanging. The fix to that is very simple. Once you figured out what's wrong, you can modify your probes to do exec with a command that uses the standard command line utility timeout, and be sure to preserve the status, and then move your timeout seconds from this YAML declaration into the timeout command. And this works perfectly every time, and we haven't had any problems with that. Okay, this was a surprise to me. You're all aware of deployments and stateful sets in Kubernetes are, actually I should say, services in Kubernetes can point at pods that may be in a deployment or a stateful set. And you think that the feature set that's there is good enough to give you zero downtime pod restarts or zero downtime upgrades. We learned the hard way that that's not the case. Because the service object and the deployments or the stateful sets are decoupled from each other, when pods in the deployment or stateful set start to go down, it takes a second for the service to realize, oh, I should remove that from the load balancer. And you would think, like a good, well-researched dev, of course I know what to do. I'll use termination grace period. This is provided. It tells the pod how many seconds to wait before completely going away. And so you would think, yeah, that's perfect. Whenever a pod's going to be removed, we say, that's fine. We'll wait 30 seconds. Connections will drain out, and then we're done. Except the sequence of events is not like that. What happens is you get the termination signal. SIGTERM comes immediately. So your application, in our case, a database, but it could be any kind of application, immediately begins to shut down, which in most cases means stops accepting new connections. Meanwhile, so I'm inside my termination grace period window here. Maybe I've got 30 seconds that I gave myself, but I'm already shutting down. Meanwhile, the service is sending me potentially new connections via the load balancer. This was, having researched it, I see that it's the only way Kubernetes could work, but this was extremely surprising to us. Even more surprising was that the only really good way we could think of to overcome this is to add a pre-stop hook to every pod that we care about zero downtime upgrades and restarts, to just say, before you send SIGTERM, just sleep for a while. Just hang on, it's fine. And then during that sleeping window, you're removed from the load balancer, and then no new connections come. You get the SIGTERM, you start to shut yourself down. Any connections that are in progress, most databases will gracefully finish working on, and your termination grace period starts to apply at that point. So that was surprising to us. We thought surely there's something better we can do than sleep 30. I mean, it looks like, bringing a stone axe to a gunfight. But in the end, we realized you can't actually know, even if you watch connections come in, how can you know that that's the last one you're ever going to see? How can you know if you go to the zoo, this is the last time I'll ever see a giraffe, I should savor this moment. And so we decided you can't, and would just sleep for 30 seconds. Another problem with stateful sets is they are slot-based. So if you've worked with them, you know that pods are numbered, foo-0, foo-1, foo-2. And as you add pods, that number goes up. As you replace pods, if you delete the 0 pod, you get another pod named -0. You don't get a pod at the end. You get that same slot filled. It's good because the stability of names is very convenient. For deployments, you get these kind of random looking names. They're hash based, but you can't predict what they'll be, which means that all the coordination, cluster formation, and that sort of thing has to be done through services, which you might not strictly need if you had a stable name. So the fact that stateful sets give you a stable name is convenient and nice. But there's some problems. So suppose I had a 3-node cluster and I want to replace a pod, but I don't ever want to go down to 2 nodes. I want to stay at 3 or more. The way a deployment can handle this in Kubernetes is to spin up that 4th pod, and then only after that one becomes healthy to begin spinning down the pod that was to be replaced. But stateful sets don't exactly have this luxury because the slot is the slot. So if I say I want to delete 0 and I don't indicate that I want more pods, then the behavior is always to take 0 away and then put 0 back, which means I failed. I went from 3 to 2 and then back up to 3. So what would it look like if you wanted to do this yourself? Because sometimes we want to. Here's what we have to do. We have a stateful set and we have a count of 3, and we'd like to replace the 0th pod. The only way to do this, because of the slots, is to create a new pod, pod 3, wait for replication. Remember, these are databases, it's not stateless, so we have to copy potentially terabytes of data around. This could be hours. Then we decommission pod 0 and wait for any leadership transfer, any final replication that might need to occur. And now at this point, it's safe to recreate pod 0, and it'll come up. It's got a new PVC potentially, so it may have to completely replicate from scratch, or it might have been down for a while. And then at that point, we have an extra pod. We don't want 4, but we needed 4 to get this done without going below our service level. So now at this point, we have to decommission pod 3 and then wait for leadership transfer and re-replication that might need to occur from that action. So all told, 8 steps to do what a deployment can do in what appears to be 1 step. It would be nice, and I'm showing you now something that doesn't exist, but it would be nice to have this, somehow to have a stateful set which would allow us to create that pod 3, but maybe not somehow not call it pod 3. Like I want to call it pod 0 replacement and let it replicate and let it get ready, but not be in service. And then at the last moment, swap it in with pod 0 so that pod 0 goes away and can be decommissioned offline, but we don't have to wait and we don't have to do 8 steps waiting for all this to happen. Most of these are things that can help you. This one's just purely a complaint, I'm sorry. So if anybody can change this, please do that. All right, one thing we discovered is that stateful sets, one for a database cluster really isn't enough. You can't partition a single stateful set across failure domains. So in AWS, this means an availability zone. There's nowhere good to specify, I want the 0 pod and the 4 pod to wind up in zone A, and I want 1 and 3 to end up in zone B, and I want 2 and 5 to end up in zone C. There's just nowhere for you to hang that information that Kubernetes could really understand it. You can schedule pods in that way into failure domains, no problem in Kubernetes, using labels and taints and affinities and that sort of thing. But because a stateful set operates in a single template, you can't do it within a single stateful set. So, right, the template can only have one definition, and there's no way to substitute things in. So here's a scenario why this maybe is not a great thing. A naive stateful set, if you spun up 6 pods, could look like this. We got pod 0, 1, 2 in ABC, and then we got pod 3, 4, 5 in ABC. That's fine, we got a good placement. This is the default behavior, it seems, of Kubernetes, is to spread things across failure domains. That's wonderful. But suppose the reason for failure domains actually comes into play. Suppose we lose zone A. And further than that, let's suppose that we were near capacity when that happened. So we lost pod 0 and 3, but we really need that capacity. You know, we're not going to be able to meet our goals with only 4 and not 6. So the best thing we can do in this case is to provision 2 more to increase the replica count in the stateful set and provision 2 more, which if we're lucky, I think probably the behavior, we haven't actually simulated this, but I think probably the behavior is you get the pods in zone B and zone C since zone A is down. That's fine. We'll have replication that'll be happening. We'll experience degradation. What can you do? But eventually we'll recover. Zone A is down. B and C are still up. But now zone A comes back. And that's good. We got pod 0 and 3 back. They will rejoin the cluster. They'll get the ranges that they're in charge of. Everything will be wonderful, except now pods 6 and 7 are weird. And you have to decide, what do you do? Do you tolerate the weirdness? What if another zone goes down and more weirdness occurs? You know, at pods 8 and 9, if zones B went down, you could get like an accumulating effect of imbalance. And at some point you might have to do a lengthy rebalancing operation to get everything back in so that the round robining performed optimally. And this may seem like just an annoyance, but in a slide or two, maybe the next slide, we'll talk about a way that this could become an event for you.
Hi, Chris. A couple questions for you.
Sure.
First is, I noticed you talking about different availability zones. Have you explored deploying multi-region Kubernetes clusters? Is that on your roadmap at all?
It's on our roadmap. I think we'll probably get to it later this year, but we haven't done a lot of work there yet.
Okay, good to know. And then we have one question from our audience. It says, it'd be nice to share the deployment architecture and what services are provided. Specifically, are these enterprise services or customer-focused services? And how do you manage the quote-unquote global provisioning of those services?
I see. So yeah, all our provisioning, I may have to have you repeat the first part of the question, but I'll answer the second part. All these are provisioned at the moment for microservice development only for production. Right now, new workloads are coming online that are for analytics. And as we kind of move out of, so this was all built for consumer electronics, which is just one division of Bose. But the goal is for our platform to become the kind of go-to solution at the company so that other divisions don't feel like they need to build their own. And at that time, I would expect the workloads to become more and more diverse. But at the moment, it's all basically online transactional for microservices for consumer electronics. Even now, we're starting to see more diverse workloads, and it's all for internal customers. There's some crackpot long-term plans that might make some of this no longer applicable, but I'll just talk about what's there today. What was the first part?
The first part was around just sharing the general deployment architecture and what services are provided.
Okay. So the services I provided, well, so the databases are that I listed earlier, which are, see if I can do it from memory, Cockroach, Elastic, Kafka, Mongo, Redis, Postgres. Those are the ones that we provide as a DBaaS team today. There's some talk of other people using our architecture to provide other kinds of services, but we hopefully will never be in charge of managing that. If anything, we would like in-source our tooling and allow other teams to use it. The architecture we use to deploy it, to provision these things, is the service catalog is out front, acting like an operator in Kubernetes terms, which means that it uses API aggregation to have a new resource type in Kubernetes, and users interact with that resource type. So that's where the actual specification of, I want a Cockroach, I want a Redis, happens through those resources. Then behind the scenes from that, the service catalog calls into what are called brokers. These are the things, this is the main area where we did work, things that we wrote ourselves. And so for each database type that we provide, there is a broker that understands how to provision all of the different plans for that database type and how to upgrade from plan to plan, or how to modify an instance when parameters are changed, say CPU or memory. So in our case, there are 6 or 7 brokers There are a couple of extra ones that I don't mention because they're not really production ready. And those are what are fielding the requests from the service catalog. The service catalog as an operator kind of operates as the same kind of state resolution mechanism that a stateful set does, or a deployment, where it looks at what the state of the world is and then tries to bring it closer in line with what the user has asked for. And the way it does that is to make RESTful HTTP calls into the brokers and say, hey, I noticed there's no database here in this namespace. This guy asked for one, would you please put one there? And the brokers do their best to do that work and report back to the service catalog that it's been done. Everything else is really just templating and the application of Kubernetes, standard Kubernetes resources. We do stateful sets, network policies, services, really almost any kind of resource that's in the standard toolkit, as well as we create backup schedules through Velero and one-time backups. Those are two different kinds of custom resources that Velero supports.
Awesome. Thanks so much, Chris.
All right. So backing up a little bit, we just talked about a weird scenario where we became unbalanced, and maybe we're not so happy, but it doesn't feel like such a big deal. We can take pod 7 down, we can take pod 6 down, and we'll be back to balanced. But there's a wrinkle. Suppose zone A comes back, and we're happy, everything's back up. And we've decided to get rid of these extra pods. We don't need them anymore. Our load is perfectly satisfied by 6. We don't need 8. So we begin to decommission pod 7. If the amount of data is big, this could take a while. This could take, in the case of some of our Elastic work, it could take 12 hours to fully rebalance, without changing the settings, without potentially impacting the performance of the rest of the cluster. It might take a very long time to rebalance. That's fine, you think we're handling the load. But what happens if you need to scale up during the operation where you're trying to scale down? Unfortunately, the kind of naive behavior you get is, let's say that you're in a pre-stop hook. You're not just sleeping. You are instructing Elasticsearch to egress all of its data and move it onto other nodes in the cluster. The pre-stop hook can't easily be stopped. I mean, it's not that you couldn't stop it. You probably would have to log into the Kubernetes worker node that had the database on it and manually kill the Docker container. This is like pretty rude, and I wouldn't recommend going around doing things like that to live databases. But it highlights a problem in having just a single stateful set and dealing with scale down and scale up operations that take a lot longer than what they might take in a deployment. In the stateless world, where containers can spin up and down, a very long, a very slow to boot container maybe takes 5 minutes. Maybe you could say we stretch that to 10 minutes. But a very slow database container that needs to abdicate all of its data to someone else, it could be hours. And so if you're stuck scaling down for hours and you need to handle a load that's coming in the next 5 minutes, what do? You're forced to react to these blunt instruments. So that's a place that can bite you. When it seems like it was merely an inconvenience, it can become an event. And then finally, about stateful sets, shutdown of a pod has really no semantics. I think this makes a lot of sense, again, for stateless pods. When you're going away, what are you going to do? You're a nameless, faceless pod among many nameless, faceless pods. And what could you do on shutdown that's so different from someone else? But in a stateful set, you're not a nameless, faceless pod. You're data node number 3. And on you, there's this subset of data that's, you're responsible for. Hopefully that's replicated to other pods. But at the very least, you need to get rid of your ownership of that data and possibly wait for some replication to happen so that the cluster doesn't go into a degraded state. So there's all that's going on. But part of the problem is, and the reason it's difficult to make good decisions about what to do while you're shutting down, is you're not sure why. am I being shut down because the node I'm on is being drained for maintenance? In that case, I just probably want to shut down and let Kubernetes reschedule me, and my volume will follow me, and I'll come back and it's like nothing ever happened. But I don't know that that's why I'm going down. Maybe the pod's being rescheduled for some other reason. Kubernetes can, if it's configured to do it, can evict pods that are on nodes that are too busy and try to move them to nodes that are not as busy. And again, in this case, you just want to quietly go down, leave your volume alone, leave your potentially some of your ownership alone, and be reinstantiated on another node where you can pick up where you left off. The replica count might be decreased, which is a user action. And again, you have no way to differentiate this from either of the two conditions I mentioned before. It looks like to you that you just got sig term and you're supposed to do that sig term thing you do. But it might be that your replica count is going down temporarily while some maintenance is being performed, or it might be that your replica count is going down for good and that you were a 5-node cluster and now you're a 3-node cluster, and the two pods that are dying should completely clean themselves up and maybe be decommissioned automatically rather than just going down thinking that they'll restart. So it's a little problematic that Kubernetes has some of this information, but doesn't, as far as I know, doesn't communicate that to you. Right, so is this an ephemeral thing or is it durable? And then finally, to fully automate this, we and you and I think anyone would need to communicate a little more with yourself to indicate what's going on. The way that we do this is to annotate pods that are going down for good before they go down. And that way they can view their own metadata and decide to do something different. So in that case, they would decide to completely decommission themselves rather than just go down expecting to come right back up. This is an okay solution. I'm not nuts about it because there's no way to use the Kubernetes machinery to really do this automatically. You have to have some process somewhere that understands what's going on and updates annotations. And then your pods have to be quite aware that they're running, that they're a container in a Kubernetes cluster and that there's a certain annotation that's very interesting to them and that might change their behavior. So that seems a little unclean to me, and it would be nice if Kubernetes could communicate more about the reason for a scale down. So having said all this about single stateful set and the problems that it can present, a solution that we have in mind is that maybe you should run more than one. 5 minutes. Let me quickly get through this. So if we run a stateful set per failure domain, we get around some of the problems that we mentioned before. It means that during a domain outage, we can scale the other stateful sets up and down independently. And if we want to decommission things out of the stateful sets that we have scaled, it's not a big problem. It allows scale to be increased during a decommission operation. As long as you only ever decommission on one stateful set at a time, the other n stateful sets, or n-1, could have their scale increased to handle an unexpected load. And then finally, it makes it a little easier to connect clients to a node that's on the same failure domain. So if you wanted to connect a Zone A client to a Zone A database node, having them separated this way makes it a little easier. But of course, everything has downsides. Now you're in the scheduling business. You have to decide where to put things. You have to decide if someone says, I want 8 nodes spread across 3 AZs, which is the AZ that gets 2? And that policy decision can be quite simple, but it has to be expressed somewhere. Now we are doing something that feels to me like it should be the orchestrator's job. And it's just features maybe that are not ready yet, but every time you adopt some functionality that's beyond what's provided, it becomes a liability to you. Helm charts that are available will never teach you how to do this. All the public examples of Kubernetes resources don't mention anything, as far as I have seen, that's very much like this. So you're on your own if you decide to do something like this. And then finally, for database technologies that depend on multiple node types, so Elasticsearch has masters and clients and data nodes, or Mongo has Mongo S, Mongo D, and Mongo C. In those cases, the fact that you might want one stateful set per failure domain means that you could end up with a stateful set where you have the number of node types times the number of failure domains, which if everything's automated perfectly, maybe it doesn't matter that much. But in an emergency, I'm not sure I would love to manage individually like 9 separate stateful sets and decide, oh, which one's going to go up and down at this time. So it's a thing that we're pursuing, but I think there are going to be almost as many problems here as solutions. And then finally, something that is coming out now, it's becoming more and more popular, are operators that handle all this stuff in a more database technology specific way. So there's kubedb, which is out and has been improving a lot. Rook, which we've just barely started to look into. Elastic has the Elastic Cloud on Kubernetes, which is in alpha now, I think. And ideally, some of the benefits here are that a well-written operator could handle everything. It knows exactly how Elastic works, and it doesn't have to do the slot-based thing. It can, rotate pods freely. Another benefit, it's probably going to be written by an extreme expert. You don't have to learn everything you need to know because it's already been learned by the people who wrote the database. But again, downsides, very few of these exist now. It's a new idea. The development is young. It would be possibly risky to adopt things that, could not have possibly been in production for more than a year yet. So the solution may be coming, but to me, it feels like it's not quite there yet. And then it may or may not be easy to integrate this with the rest of your stack monitoring or whatever else you have, CI/CD, especially when you start to think about what would it look like to run kubedb, Rook, and Elastic Cloud together and try to provide a uniform interface. So anyway, that's upcoming. I expect in the next year or two, this solution space will firm up a lot, and it may be an obvious choice to move to. I think that's all I've got. Thank you very much for your attention. Nate, if you've got anything, then you can do that.
Yes, so thanks everyone for joining. Charlotte, one of the Cockroach Labs team members, will be sending out a survey. We'd really appreciate it if you fill it out. It just helps us get better every single time. I just want to thank everyone for attending. And Chris, thank you so much for sharing what you've learned with Kubernetes and building a database as a service on top of it.
It's been a pleasure.
Thanks so much. All right, bye everyone.